Section 9.4, Solving Quadratic Equations by Completing the Square. So what we're going to look at in this section is a different way to solve a quadratic equation. It's convenient if we have the equation written that involves just one variable x, either being squared or being added or subtracted to something, and then having that value be squared. When we have an equation that includes an x squared and an x term, it's not always easy to solve. So one method that we can use for solving these types of equations is called completing the square. Here we have a visual representation of what that is going to look like. We'll start off with an expression that is x squared plus bx. We're going to ignore the constant for right now. This expression, which is not an equation yet, can be transformed to make it into a square instead of the rectangle that it is originally. But in order to make it a square, I start with the square that's in the corner, and I take my rectangle and I break it in half. By rotating the second piece and fitting it in on the bottom of the square, I've created this shape here, which is not a complete square, but it's more of a square than I had before. In order to complete the square, I'll need to add in a little square here at the bottom. Now you can look at the labels on this here and see that we originally have a square that's x by x and a rectangle that's x by b, which gives us x squared plus bx. And we also have cut b in half so that the length is now b over 2 when the width is still x, and the same thing over here. And therefore, because these lengths are both b over 2, the value in here would be b over 2 as a quantity squared, which we could rewrite as b squared over 4. Anyways, the idea is that in order to take this rectangle and make it a square, I'm going to cut the rectangle in half, the other part of the rectangle in half, move it around, and then just add in a square at the bottom. So let's see how this works. So I'm going to start here with part of an expression, x squared plus 6x. I've shown this also in algebra tiles. I have my blue square, which is x squared, and I have 6 green rectangles, which represent 6x. And so those just representing the x squared plus 6x. I want to take this, as now it's currently a rectangle, and I want to transform it into a square. I'm going to start by rearranging some of my blocks. So by taking those 6 x's and cutting that in half, I've moved them around now so that I have 3 x's along the x squared that way and 3 x's along the x squared this way. It's still the exact same expression, x squared plus 6x. It's just moved around a little bit. Now I just need to figure out what would go into this space here. Well, these are each x's, or 1's, with the length of x being here. And so a bunch of 1 by 1, this is going to all be filled in with a bunch of 1's, 9 to be exact. By adding in these 9 yellow squares, which are each representative of 1 unit, it's the same as adding 9 to my original expression, which brings me to x squared plus 6x plus 9. Now that expression, much like this, is factorable, and I can see what that's going to look like if I just fill in the outside, top and left, of this algebra tile grid. So now you can see that we can fill in the exact same thing on both the top and the bottom. 1x and 3 little 1's, which means that we can express this as either x plus 3 times x plus 3 or as x plus 3 squared. And so what we did is we started with the original expression and we added something to it in order to complete a perfect square. Now, the one thing you should know is that this x squared plus 6x is not identical to the x plus 3 squared. We had to add 9 to it, so we had to change it in order to make it a perfect square, but we did complete a perfect square as a result of our efforts. So what we're going to do is we're going to start with an expression, x squared plus 4x, and we're going to try to complete the square. In order to do this, we're going to follow these 3 steps. Step 1 is to find 1/2 of b, the coefficient of x. So I can see here that my b equals 4. That's my coefficient of x. So I need to find half of that. So I do 4 divided by 2, which is 2. And then step 2 says to square the result from step 1. So I'm going to take that 2 and square it, and that's going to equal 4. It won't always come back to the value that b was originally. This is just one particular example where it does. And I'm going to add that to this answer of 4 to my expression. So I'm going to add 4 here. So I'm looking at x squared plus 4x plus 4. And when I do that, I'm able to actually factor the resulting expression. Now, I could think of this kind of the old-fashioned way and say what two numbers multiply to 4 and add up to 4 and get 2 and 2, which would be x plus 2 times x plus 2. But I could also realize that I've chosen this number so that it works out perfectly to make a perfect square. It's going to be x plus 2 squared, and this plus 2 will actually always come from my result after I divide my b by 2. And so what this has done is by adding 4, I've been able to take x plus 2 squared, which is a perfect square, and that's a completed version of x squared plus 4x. I started with some start of an expression, and now I've made it into a perfect square, which is going to be useful going forward. All right, wanted to look at 3 examples because they might be kind of tricky examples, something to think about here. For the first example here in the top left, x squared plus 7x, my coefficient of x is 7, so I'm going to be doing 7 divided by 2. Now, we're probably better off here not using a decimal. Don't use 3.5. You know, you're better off probably using 7/2. It's not always true, but for the most part it will be. Now we'll take 7/2 and we'll square that. We have to square the result after we cut it in half, and that's going to be 49/4, because it squares the 7 and it squares the 2. That's what I add to each side. I'm sorry, that's what I add to my expression. I'm going to add 49/4 to that expression. And now this is actually going to be factorable, and it's going to be factorable into a perfect square. It's going to be x something squared, and that something, remember, always comes from my result after I divide by 2. So this is a 7/2, so I'm going to put that right in there. X plus 7/2 squared. And if you ask me, using that shortcut's a lot easier than figuring out what two numbers multiply to 49/4 and add up to 7. But we have now completed the square for that example. All right, let's take a look at the example on the top right, x squared minus 12x. The only difference here is that we're using a negative, but I have to consider that negative when I'm figuring out my value here. I'm going to first take negative 12, divide that by 2 and get negative 6. And then I take my negative 6 and I square that. Now it's important to square the negative 6, which is going to give me positive 36. And so what I'm going to add on to my expression here is a plus 36. When I do that, that's going to be factorable, again using the perfect square. I'm going to start with an x, and my constant is going to go with it. It's going to come from here, and this time I'm going to include the negative. So it's actually going to be x minus 6 squared. You could check by foiling that will bring us back to x squared minus 12x plus 36. So once again, we completed the square. Final piece here, x squared plus 1/2 x. My coefficient of x here, my b, is 1/2. Now to do 1/2 divided by 2, some people struggle with that. So there's an alternative there. Rather than dividing by 2, you can multiply by 1/2. And multiplying by 1/2 will give me 1/4. Then I'll take that result and square it. 1/4 squared is 1/16. So the 1/16 is what I add to the end. And now that's going to factor. Once again, perfect square. Start with an x, and then add in the result when I divided by 2, or in this case multiplied by 1/2, and that's a positive 1/4. And so those are my factored versions of my completed squares. Keep in mind they're not exactly the same as my original statements, my original expressions, but I completed them by adding a constant to each end. We're going to see now why we would bother to do this. So now let's put completing the square to use. We can solve a quadratic equation by completing the square, and what's convenient is if we actually have it set up as x squared plus 8x equals 9. We have that x squared plus bx on one side of the equation and the 9 on the other. And so what I'm going to do is I'm going to complete the square on the left side of the equation. So I ignore the 9 for a second. I look at x squared plus 8x. So I'm going to take the 8, which is my coefficient of the x, divide by 2. That gives me 4. Then I take that 4, square it, and I get 16. So what I'm going to do is I'm going to take my original equation, x squared plus 8x equals 9, and I'm going to add the 16 to the left side of the equation, because that's how I complete the square. But if I do something to the left side, I also have to do it to the right side. In this case, I also have to add a 16 to the right side. This makes my equation x squared plus 8x plus 16 equals 25. And now, because I've completed a square on the left side of the equation, I can factor that pretty quickly into x plus 4 squared equals 25. And now this looks like exactly the same type of problem I had in section 9.3. I can solve this by using the square root property of both sides. Take the square root here and the square root here, and I'm left with x plus 4 equals, now I have to remember my plus or minus, 5. Subtracting 4 from each side of the equation and putting that in front of the plus or minus gives me negative 4 plus or minus 5. Those are my two solutions. Now, because those are numbers that I can easily combine, I want to express them as two different answers that are specific. My first answer would come from negative 4 plus 5, which would give me x equals 1. My second answer would come from negative 4 minus 5, which would be x equals negative 9. And those are my two solutions. So by having it set up in a nice convenient manner, we were able to complete the square and then solve based on the square root property we learned in the last section. All right, let's try this again. Let's see what we can do here. In this first example, I'm going to take my negative 5, divide it by 2, and that's going to give me negative 5 over 2. I'm then going to square it. And because it's a negative squared, it becomes a positive. I square both the numerator and the denominator, and I get 25 fourths. So what I have to do is I have to add 25 fourths to each side of this equation. So my new equation becomes x squared minus 5x plus 25 fourths equals negative 6 plus 25 fourths. The left side of my equation is now factorable. And it's going to be factorable into x, go back to your step after the dividing by 2, minus 5 over 2 squared equals, now negative 6 plus 25 fourths, I'd have to get a common denominator, which would be 4. So I could write negative 6 as negative 24 fourths, which combined with the 25 fourths would be 1/4. Now I'm just going to take the square root of each side, and that's going to give me x minus 5 halves equals, don't forget the plus or minus, and we have a fairly convenient situation here because we have the square root of 1/4, that's the square root of 1, which is 1, over the square root of 4, which is 2, so we're looking at plus or minus 1/2. Now I'll add the 5 halves to each side, and I'm going to get 5 halves plus or minus 1/2. And I actually have a common denominator there, so I can just write that as 5 plus or minus 1 over 2. I'm just going to give myself a little bit of space here. So I can write my final answer. I can actually figure out those two numbers pretty easily. 5 plus 1 would be 6 over 2, which would be 3. And then 5 minus 1 would be 4 over 2, which would be 2. So my two solutions there are x equals 3 and x equals 2. Those are my two solutions. Let's do the same process for the other problem and just see what happens there. Start with my coefficient of x, divide by 2, that gives me 6. Square that, gives me 36. That's what I'm going to add to each side. So I'm going to get x squared plus 12x plus 36 equals negative 16 plus 36. The left side factors, again, into x plus 6 squared. Once again, that plus 6 coming from this step here. And that's going to equal, let's see, negative 16 plus 36 is going to be 20. And now I have it set up in a nice format, so I'm just going to do the square root of each side. X plus 6 equals plus or minus. Now the square root of 20, remember, can be written as the square root of 4 times the square root of 5, so I can simplify that to be 2 square root of 5. Now subtract the 6 from each side and put it in front of the plus or minus. It's the most convenient way. And I don't need to separate this into two different statements because they can't be combined any further. Negative 6 and 2 square root of 5 are not like terms, so I can't combine them any further. There's no reason to break them up. I can express that as my final answer. I'm not interested in decimal approximations for this. I like the exact nature of the answers that I have. So, sometimes we have to do a little bit of work to clean up our equation before we can complete the square. If we have our equation in standard form and we have a lead coefficient other than 1, we have to do a little bit of work. We'll start by adding the c, the constant term, to the other side. In this example, 4x squared plus 8x minus 15 equals 0. I'm going to add 15 to each side. That's going to make my work 4x squared plus 8x equals 15. Now I need to divide everything by a in order to make this work. So I'm going to divide everything, all three terms, by 4. That's going to bring me to x squared plus 2x equals 15 fourths. Usually better off keeping it as a fraction as opposed to a mixed number or decimal, because we'll be working with square roots. Now I can do a little bit of side work here, and I can complete the square on the left side now because I have x squared plus 2x. So I take my 2, divide it by 2, and that's 1. Square that 1, and that's 1. So I'm going to add 1 to each side here. Add 1 on the left, add 1 on the right, so that the equation remains balanced. X squared plus 2x plus 1 is going to equal, now 15 fourths plus 1 is 15 fourths plus 4 fourths, which would be 19 fourths. The left side of my equation factors into be x plus 1 squared, which is 19 fourths. And now I'm going to be able to take the square root of each side. So by doing that, I'm just going to move that to over here. That's going to give me x plus 1 equals, now the square root of 19 fourths, I can split that up so it's the square root of 19 over the square root of 4. The square root of 4 is just 2, so that's convenient. I have to remember my plus or minus. Now, if I had a square root still in my denominator, like if my denominator was the square root of 3, I'd have to rationalize that, but in this case it works out conveniently. And then finally, just subtract the 1 from each side, and you get a negative 1, put it in front of the plus or minus, and you get square root of 19 over 2. If you want to get a common denominator, you can, but it's also fine to just leave your answer like this. If you found a decimal approximation, it would be a messy, messy decimal, but you could do it. It would work out just fine. And that's what it comes down to. That's how you complete the square if you have a lead coefficient other than 1. All right, one last problem for you to try yourself. Use the last example as a basis for this, and pause the video, try to work it out, and then come back to check your work. Okay, let's see how you did. All right, so there you go. You can check your work. Your two solutions should end up being 1 and -3. You could plug those back into the original equation. It would make it true. But if you want to pause the video to check your work, you can do that at this time. Otherwise, hope this has made a lot of sense.